GPT-4 has 1.7 trillion parameters. LLaMA 3 was trained on 15 trillion tokens. These numbers get thrown around constantly. But what do they actually mean? Here's the thing. Most developers using LLMs every day have no idea what's happening between their prompt and the response. They treat it like magic. But understanding the mechanics, even at a high level, completely changes how you prompt, how you debug, and how you architect AI-powered systems. In the next 12 minutes, you're going to understand LLMs well enough to explain them to your team. No PhD required. Strip away all the complexity, and an LLM does exactly one thing. It predicts the next word, or more precisely, the next token. You give it the capital of France is, and it calculates the probability that the next token is Paris versus London versus banana. That's it. Every philosophical discussion about AI consciousness, every impressive code generation, every hallucination, it all emerges from this deceptively simple task. Predict the next token, over and over, until you hit a stop condition. LLMs don't see words, they see tokens. A token might be a whole word like the, a word fragment like ing or tiun, or even a single character for rare words. The sentence, tokenization is fascinating, becomes 5 tokens. Tokenization is fashion-ating. This is why token counts matter for costs, why some words confuse models, and why solid gold Magyarkap once broke ChatGPT. Different models use different tokenizers. GPT and Claude don't split text the same way. A token is just an ID number. Paris might be token 1234, but numbers don't capture meaning. So we convert each token into an embedding, a vector of hundreds or thousands of numbers that positions it in a high-dimensional space. In this space, king minus man plus woman roughly equals queen. Similar concepts cluster together. These embeddings are learned during training. The model discovers that happy and joyful should be neighbors, while happy and tungsten should be far apart. Before 2017, language models processed text sequentially, word by word. Then Google published Attention is All You Need and introduced the transformer. The key innovation? Process all tokens in parallel and let them communicate through attention mechanisms. This made training dramatically faster. You could throw thousands of GPUs at the problem. It also let models capture long-range dependencies that recurrent networks struggled with. Every major LLM today, GPT, Claude, LLaMA, Gemini, is built on transformers. Attention is the secret sauce. When processing the word it in the cat sat on the mat because it was tired, the model needs to figure out what it refers to. Attention lets each token look at every other token and decide how much to focus on each one. For it, the model learns to attend strongly to cat and weakly to mat. This happens through learned query, key, and value matrices. Think of it like a database lookup, where the query asks, what should I pay attention to? And the keys say, here's what I represent. One attention pattern isn't enough. Bank could mean a financial institution or a river's edge. Context matters differently in different ways. Multi-head attention runs multiple attention mechanisms in parallel, each learning to focus on different relationship types. One head might track grammatical structure, another might track coreference, another might capture semantic similarity. GPT-4 uses 96 attention heads. Each head sees the same input but learns to extract different information, then they're combined for richer understanding. A transformer stacks many identical layers. GPT-3 has 96 layers. Early layers capture basic patterns: syntax, common phrases, local context. Middle layers build intermediate abstractions, entity recognition, relationship detection, basic reasoning. Deep layers handle high-level reasoning, complex inference, world knowledge application, nuanced generation. Each layer refines the representations from the previous layer. It's like the visual cortex. Early neurons detect edges, later ones detect faces. Deep transformers detect sarcasm and logical fallacy. When someone says GPT-4 has 1.7 trillion parameters, what does that mean? Parameters are the learned numbers, the weights and biases that define how the model transforms inputs to outputs. They live in the embedding matrices, the attention weight matrices, the feed forward layers. More parameters generally means more capacity to memorize patterns and perform complex reasoning. But it's not just size, how you train matters enormously. LLaMA 7B can outperform some 70B models on specific tasks because of better training data and techniques. Pre-training is where LLMs develop their base capabilities. The model sees trillions of tokens from books, websites, code repositories, and academic papers. Essentially, a snapshot of human knowledge. The training objective is simple: predict the next token. But doing this at scale on diverse data teaches the model grammar, facts, reasoning patterns, coding conventions, and even some common sense. This phase is enormously expensive. Training LLaMA 2 cost an estimated $25 million in compute alone. It's why only a handful of organizations can train frontier models from scratch. Pre-training creates a capable but unrefined model. It can write Nazi propaganda as easily as poetry. It's just predicting likely text. Fine-tuning adds specialization and safety. Instruction fine-tuning teaches the model to follow directions using carefully curated prompt response pairs. RLHF, reinforcement learning from human feedback, trains the model to prefer responses humans rate highly. This is how base models become assistants that refuse harmful requests and try to be helpful. It's also why jailbreaks work. They're exploiting the gap between base capabilities and fine-tuned behavior. When you send a prompt, inference begins. The model processes your entire input through all transformer layers, building up contextual representations. Then it predicts probabilities for the next token. Here's the key. It doesn't pick the highest probability token deterministically. Sampling strategies add controlled randomness. Greedy decoding always picks the top token. Fast but repetitive. Temperature scaling adjusts probability distributions. Higher temperature means more creative but potentially incoherent outputs. Nucleus sampling picks from the top tokens covering P% of probability mass. Temperature is your creativity dial. At temperature 0, the model always picks the most probable token. Great for factual tasks, but boring for creative writing. At temperature 1, probabilities are used as is. Above 1, the distribution flattens. Rare tokens get boosted, outputs become more surprising and chaotic. For most developer tasks, 0.2 to 0.7 works well. Coding? Keep it low. Brainstorming? Crank it up. This is why the same prompt gives different outputs each time. It's not bugs, it's intentional sampling randomness. Every LLM has a context window. The maximum tokens it can see at once. GPT-4 Turbo supports 120K tokens. Claude 3 goes to 200K. This sounds huge, but there's a catch. Attention is quadratic. Doubling context length quadruples compute cost. Also, models don't use long context perfectly. There's a lost in the middle problem, where information buried in the middle of long context is often ignored. For developers, this means put critical information at the beginning and end of prompts, and don't assume the model remembers everything in a long conversation. Hallucination isn't a bug, It's inherent to how LLMs work. The model predicts plausible sounding text, but it has no ground truth database to verify against. Ask about a real paper, and it might invent a citation that looks perfect but doesn't exist. It's optimized to be fluent and confident, not accurate. Training on internet text means it learned to write authoritatively even when humans were wrong. Hallucination rates drop with better training and RLHF, but they never hit zero. For developers, this means always verify critical facts, implement retrieval augmentation for knowledge heavy tasks, and design systems that acknowledge uncertainty. Not all LLMs are equal, and understanding model families helps you choose. GPT-4 from OpenAI excels at reasoning and broad knowledge, but runs only on their API. Claude from Anthropic leads on long context tasks and tends toward caution on sensitive topics. LLaMA from Meta is open weight. You can run it locally, fine-tune it, and inspect it, but you handle your own infrastructure. Mistral offers efficient smaller models. For developers, closed APIs are easiest to start with, but open models give you control, privacy, and no per token costs at scale. Different tasks favor different families. So what does all this mean for your code? First, prompt design is architecture. Understanding tokenization and attention helps you structure better prompts. Second, temperature and sampling aren't magic. Tune them for your use case. Third, context window limits mean you need chunking strategies for long documents. Fourth, hallucination is guaranteed. Build verification into your pipeline. Fifth, model selection matters. Don't default to GPT-4 for everything, when a fine-tuned 7B model might be faster, cheaper, and better for your specific task. LLMs are tools with specific mechanics, not magic black boxes. The field is evolving rapidly. Mixture of experts architectures activate only parts of the model per token, making larger models efficient. Multimodal models handle images, audio, and text together. Smaller, specialized models are outperforming generalists on specific tasks. And the line between retrieval and generation is blurring with RAG systems. For developers, the message is clear. The fundamentals matter. Transformers, attention, tokenization, and sampling aren't going away. They're becoming more sophisticated. Understand these building blocks, and you'll adapt to whatever comes next. Let's recap the three things you now understand. First, LLMs are next token predictors. Everything from code generation to creative writing emerges from this simple objective applied at massive scale. Second, the transformer architecture with its attention mechanisms allows models to process context in parallel and focus on relevant information, which is why prompt structure matters so much. Third, training happens in stages. Pre-training builds broad capabilities, while fine-tuning and RLHF create the aligned assistants we interact with. But hallucination remains inherent to the design. Next up in the AI track, prompt engineering patterns that actually work, where we'll take these fundamentals and turn them into practical techniques for getting better outputs. Hit subscribe so you don't miss it, and drop a comment below. What's one LLM behavior that suddenly makes more sense now that you understand the architecture? I read every comment. See you in the next one.